make sure. I don't want to do the wrong problem. I mean, dy over dx, 2xy is equal to 3y to the fourth, and y is equal to 1/2. There we go. Okay, so this thing is a Bernoulli equation because it looks linear. The big difference is this issue over here. If it wasn't for this, it would be a linear differential equation. So the idea is that we're going to make our substitution. Specifically, the substitution is that u is equal to y to the 1 minus 4. And that's, we're going to see how that works here in just a sec. So du, whoops, sorry. I need to do it this way. So there's y. This is going to be y to the negative third. So dy, du. How am I supposed to do this? Du is equal to negative 3y to the negative 4 dy. I feel like this isn't the way that we did it. Okay. All right. Well, I'll just barrel on ahead and we'll find out. Just feels wrong. Okay. Well, because this should be linear when we get done. Okay, so dy over dx, that's my concern. Let me write it out like this. Dy over dx, let's see, du over dx is equal to dy over du times dy over dx. That feels better to me. Sorry. Okay. Sorry about that. Okay, so this, here's how I want to do it. I'm sure that it would work if I just changed the du, but this is going to feel better to me. So du over dx is equal to, ooh, do I have to solve for u? Wait, are we sure this is the way I did it last time? Okay. Oh, I see what you're saying. I see, okay. Yeah, okay, like this. That feels better, okay. Sorry, it took me a, okay, I'm okay. Okay, so what we're going to do now is, let's see, I think I'm going to fabricate this, as is my want when I do any substitution. I don't like doing the substitution without having exactly what I'm substituting. So if I'm going to put that there, I better put it everywhere, which means it gets multiplied. So I've taken that, and I'm going to multiply the next thing. So basically multiply through by that negative 3y to the negative fourth. So this is going to be minus negative 3y to the negative fourth times negative 2xy. Let's clean that up. And that equals, let's see, negative 3y to the negative fourth times 3y to the negative fourth, or to the fourth, is going to be just negative 9. Doesn't that work out that way? I think so. Wow, this is still not making me happy, because I don't like the 3y to the negative fourth. Okay, well, let's barrel on ahead. Yeah, x squared, that's my fault. Okay. Oh, no, it's making me happy now. No, sorry, it took a minute. Now I see joy. Okay, so we've got x squared times negative 3y to the negative fourth times dy over dx. Sorry, the brain fog or whatever. And then I'm just going to make that a, oh, there's a triple negative. I guess it's still negative, isn't it? No, it's a double negative. So that's going to be plus. Okay, so that's going to be 6 times x, y to the negative third. I can't believe it's super slow for some reason today. My computing speed is incredibly slow. I got it now, though. So far, so good. So now we're just doing some algebra. Now that we've got this set up like this, I think we can make the actual substitution. So the substitution is that this is u, or du over dx, and this is u. Yeah. So we have x squared du over dx plus 6xu is negative 9. Now the rest of this, this is a nice linear differential equation, although on the exam, I noticed some of you still don't know how to do these, so let's work through it. To do a linear differential equation properly, you first of all have to, get your du over dx all by itself. So I'm going to divide everything by x squared. When you do that, then that 6 cancels, the 6x cancels with the x squared. So I've divided everything by x squared. Now we come up with an integrating factor. I noticed some of you used r of x. I used mu because I thought that was cool. But if the book uses r, I don't care. Let me just see what, oh, it uses mu. I'm going to use mu. So I don't know why you guys, maybe you looked on a video online. So I've seen R, that's why I wondered if I was just doing it different from our book. Our book uses mu, and so mu of x is e to the integral of whatever the coefficient of u is, or y, whatever it is. So this is 6 over x dx. And if you've done this a few times, you know what the answer is going to be. You know that the answer is going to be x to the 6th. But let's just go through the motions. This is going to be e to the natural log of 6 natural log of x. And then you move the 6 inside the natural log, so e to the natural log of x to the 6th. And then you just get x to the 6th. So that's the integrating factor. So I know we've done a substitution. Now we've got an integrating factor. So x to the 6th du over dx plus 6x to the 5th u is equal to negative 9x to the 4th. So just to explain where everything went, when I multiplied x to the 6th times 6 over x, one of the x's canceled. And when I multiplied it by 9 over x squared, two of them canceled. Okay, now at this stage, I'm going to write down everything. Some of you are skipping this step, which is fine if you get it right. But if you get it wrong, you might want to write this down. So here's how this actually works. X to the 6th u prime plus 6x to the 5th u dx. And this negative 9x to the 4th dx. So the whole point of the integration with the integrating factor is that this will be the product rule. And you can kind of see here, x to the 6th times this thing derivative, and then this is the derivative of x to the 6th times the thing there. So that when you do the antiderivative, you just get x to the 6th times u. So if you want to circumvent that and just go right to this, that's fine. Be my guest, but just get it right. Don't get it wrong if you're going to do that. And then this is going to be negative 9/5, x to the 5th plus c. And then I guess I can do this, negative 9/5 there, plus c over x to the 6th. How's that look? Now, if we want to finish this, which I think you probably are going to beg me to do, so, well, you really probably don't need it, but I will need to go back here and figure out what u is. U is y to the negative 3rd. So y to the negative 3rd is negative 9 over 5x plus c over x to the 6th. Beautiful. Do I really want to mess with this? Let's just get that initial condition. Which one was this? 21. Y of 1 is 1/2. Okay. So 8 is equal to negative 9/5 plus c. This is making me sad. 49/5. At least that's what I'm getting. I don't know if that's back of the book. I hope so. It is? Oh, good. Won't bother me. Yeah, so you could clean this up. We could solve for y. I'm just happy that I got through that. All right, anything else while we're looking at these? So that one was the Bernoulli equation. So any of the homogeneous? Homogeneous was easy. Homogeneous, by the way, it's always y equals u times x. As long as you have a homogeneous, or x is equal to v times y, but who wants to use v? V is horrible. Let's use u. So actually I gave you the hint. I gave you a hint on both of them. So Yeah, let's give this one a go. Try it out. Just a minute. Sorry, I'm looking at this thinking, why? Oh, I see what's happening. Okay. Let me help you with this. Oh, it's 3 and 4. Oh, I didn't fix my numbering. Some of you have 3 and 4. Some of you have 1 and 2. I didn't the numbering didn't restart. I hate it when it does that. But we'll give it a go. I'll put it up on the screen momentarily and help you get started with the second one. The first one should be pretty straightforward, but I can help you that one as well. There's too many. I don't know why I have so many of these. Yeah, I have way too many. So there's enough that everyone can have a souvenir, take it home with them. There's a couple for you if you want. You don't want me to. I think I must have printed them twice. I lost track. All right, I'll get it up on the screen momentarily. Just gotta dig it out of my files. All right, so the way that both, you might not have this issue, but just in case, the way that these are written, it may be a little confusing. So the top up there is um, the homogeneous, maybe written a little closer to the way it looked in the book. And then the one on the bottom is closer to what you were expecting for the Bernoulli. So I'll cram them closer to one another. I'll just move this up. There we go. Now you can see them both. By the way, if you get stuck on one of the antiderivatives, just skip it and come back to it if you have time at the end. But yeah. Which one? What about it? This here? Let's see what happened there. Oh, yeah, that should be to the fourth. You're right. Let me fix that. I got too excited. Here, this will look better. There. Second one. Sorry about that. Yeah, I messed up with my fourth power. If you've already done it with the third power, it's okay. I'll do it with the fourth power since I haven't done it yet. I don't want you guys to suffer too much. I just did both of these, and I'm sure you can do them. It's just that the integrals are not as kind as I would have hoped. This is my price I pay for just making it up and thinking, oh, it's Bernoulli, it'll be fine. So do your best, and if you have the integral, even if you don't have the antiderivative, that's like 90% of the problem, okay? So when you get to that, the antiderivative, you might notice the one I'm talking about. I don't know, just give it another few minutes. I don't want to take forever, so. Oh, you're all done. Excellent. Wow. What a writing. Yeah, this is what, that's what we're looking for. That's the important stuff. I guess you guys are handing in your homework today. Okay. I was hoping to delay this until the next day, but I guess since we have piles, I'll deal with it. I feel like I've almost recuperated and can deal with this, so this will be a good test case because I didn't collect in the other classes. All right. This one, sure, why not? Very nice. I think I'm gonna cut people off. Just hang on to this. You know what? This one is so algebraically nasty. I think I'd rather cut you off so you don't suffer anymore, and then we can move on. So let's just go over this together, and you can correct your own. And you might have gotten stuck somewhere, and you're thinking, how do I integrate this? There's just a couple of techniques. There's an integration by parts, and there's an integration by substitution that's a little bit odd. So let's just do it together and be done with it. And I'll be more careful. See, this is a good, this is part of the reason I do these quizzes. It's not just to let you have practice for when we have our test. It's for me to get some practice for when we have our test as well. So that when I get to the test, I'm going to be like, I better make sure that when this works through, we don't have anything weird going on. So anyway, and let's go ahead and see how this works out, and see if I got it right, because I don't know. I only looked at one, and I don't know if it's. So let's see. We'll take a look at this first one. I sort of say that this is homogeneous, but you could check. Just put yt in. Well, you can see when you put it in this form, you have all linear, all linear. So it's homogeneous. So you can do this for your substitution. Here's your dy, is this stuff here. And then I've just made the substitution directly in here. So double check my math, at least up till that point. Can I get it all on there? Well, I guess I have to show you the third step. So there it is. But here, all I've done is I've taken dy and I've replaced it with that thing. It's the product rule, essentially. And then I replaced the y with u times x. That's it. So I did that okay? All right, no one's yelling, so we'll assume that I did. Then at this point, I did a little bit of algebra. So let's see, what did I do? Oh, I know, I did 2 or 3 steps at once. So this is where you might want to double check. So here is all the dx. So let's double check. X times dx, negative ux times dx. This came from ux times u times dx is u squared x dx. And then x times u times dx is this one. And then over here, this was this du times x times this stuff. So I factored out the x squared, and I left u plus 1 here. So u plus 1 times x squared times du. Look okay? So you can check your own work, figure out if you did it right. And if you did, I applaud you, because this one's hard. I mean, it's a lot of bookkeeping. Okay, so then I solved, well, I moved all the x's. So I moved this over to this side, and I left this here. And when I moved this over here, you might wonder, where'd everything go? So first of all, the ux is canceled. You can see that. This is a bunch of algebra, but this cancels with that. You can factor out. So here is x, and this is u squared x. So I factored out a 1 plus u squared, and that ended up dividing. And then the x, when I moved it over, oh, I know, it became negative, but then I divided by this x squared, and that's why this is 1 over x. So I know I did like 4 steps in one here, but I believe this is all correct. So far, okay? Hopefully. Okay, so then the next step. So that's like the hard stuff. And then this is what I meant by once you have your integrals set up, that's like 90% of the problem is getting to this stage. Because then at this stage, you can do your integrals. And technically, you're just doing some Calc 2 stuff, whatever, or maybe even Calc 1. So in this case, I separated this into 2 pieces. There is u over this stuff, and then 1 over this stuff. Of course, the 1 over that stuff you recognize as arctan. The u over that stuff became this right here. So I know, I just did substitution in my head, but you'd get this. So if you do u over u squared plus 1, let w, since it's the second substitute, w equal u squared plus 1, dw is 2u du. That's where that 1/2 came from. Natural log, you recognize that. Arctan came from the 1 over u squared plus 1. And then here, of course, natural log, and then the plus c. And I didn't do much more than that. All I did was I took that and I resubstituted based on this. U is y over x, and I got all of that. So that is the final answer. But I was more and more sad the further and further I got down this. Surely I can come up with a homogeneous problem that is not quite this involved, which I will try to do. I just thought, oh, surely that doesn't look that complicated. I was wrong. So I apologize, but there it is. Let's take a look at the second one. Second one is this, now that I've got it correctly stated over here. So the u is y to the negative 3, so you just do 1 minus this. negative 3. The derivative, this is exactly like the one that we did from your homework, but the answer ends up being harder. And once again, I thought it would be simple, but apparently not. But anyway, so I rearranged this. I multiplied everything by negative 3y to the negative 4 because I wanted this to be like this. And when I did that, one of the y's canceled here, all of the y's canceled there, which is what you want. That's the whole point of this. Then once you're done with that, here's the substitution. Looks pretty straightforward until you find out that your integrating factor happens to be e to the negative 3x. Yeah, so the integrating factor here is mu is, yeah, I'm filling in the steps that I skipped earlier. E to the integral of negative 3 dx, you're using this thing, which is e to the negative 3x. So I had to multiply everything by e to the negative 3x, which is all fine and dandy on the left side because that turns into this. But on the right side, that turns into this, which is pretty ugly. Not that big of a deal, but you have to use integration by parts. I didn't show my work, so I should lose points, but there's my final answer. And it looks like that in the end. So yeah, it got worse and worse as I kept going. Yeah, because integration by parts goes there. Then this is, I multiplied everything by e to the negative 3x. Oh, it should be plus. Sorry, I see a mistake. Yeah, yeah, because I essentially multiplied by e to the positive 3x to get rid of all that. Then, yeah, I've solved for y. Another one that's not very happy. All right, we should move on. We have time, 12:47. I just feel like going to bed. No, I'm just kidding. Let's go ahead. Let's do this. Let's do this. Actually, let's do this. Someone asked me, who is this Bernoulli character, right? And I thought, oh, I'll look this up because so Bernoulli, there's a whole family of Bernoullis. I forget who it was who asked this, but they're responsible for bringing us all sorts of formulas, all sorts of physics. Maybe you know the Bernoulli principle from aerodynamics. So there's all sorts of Bernoulli stuff going on. So I looked up the family and I found some student somewhere had made a slideshow. And I thought, well, why should I have to reproduce this? Someone has done it for me. So here it is in all of its glory. I don't even know who this is, but they did a pretty good job. So you've got these 3 generations of Bernoullis. There they are. And these are the main ones that are, but all of these people were various mathematicians. So you have Jacob Bernoulli and Johann Bernoulli, and then each one, yeah, there's multiple Johanns and a couple other Jacobs, but Daniel Bernoulli is the one who did all of the physics. So anything Bernoulli, like the aerodynamics and stuff, that's this guy. And then these people were in, I think whoever did this has some, so I didn't, oh, that goes to the end. Hold on a minute. How do I go to the next? Oh, there it is. Okay, so Jacob Bernoulli. I'm just trusting that this person did a good job on this report, so I'm just going to, keep going. Oh, the isochrone. This is a cool problem that Bernoulli, as well as other mathematicians, worked on. This idea of what is the curve that creates the fastest, so from point A to point B. So imagine here, pick 2 points, doesn't matter where they are, pick a point, whoops. Oh, I can't draw on that. Here, I'll draw, this is kind of cool actually. So, so you have this and this. Oh, actually this is the brachistochrone problem, not the isochrone. Okay, so the isochrone problem is related to the brachistochrone problem. The isochrone problem is, can you come up with a curve where wherever you put the ball on the curve, it'll take the same amount of time to get to the bottom? And in fact, you can. And this is, there's a name for this curve. Well, it's a cycloid, but anyway, let's move on. Nice. So apparently Jacob Bernoulli worked on that. Probability, so Bernoulli, there was a lot of probability that Bernoulli is involved in. There's some Bernoulli probability functions. Anyway, so you have Bernoulli numbers. But the one that you're interested in, yeah, so they worked on calculus. There was rivalries. Good, good, good. Here, I'm getting to the good stuff because here it is, Daniel. So Daniel is the one who was the one who did the stuff with the differential equations, just so you know. So anyway, Daniel dealt with, let's see, Newton's rates at which liquids flow and stuff like that. So this is the viscous flow. So this is the thing that, like in aerodynamics, you have the wing. The way the wing works is because of Bernoulli's principle. So they're good enough. Yeah, whatever. I don't know. I didn't make this one. I just thought it was interesting and thought I'd bring it out here. So yeah, because someone, I forget who, asked about Bernoulli, and there's a whole bunch of them. Okay, so what are we doing today, or rather we're starting today and we're going to do on Friday for real, is we're going to look at what's called a numerical method. A numerical method, or numerical methods in general, are ways of getting computers to do calculus for us. And the reason why we're doing this now is because there are differential equations that are so hard to solve that you might say, well, you know, all I need to know is a solution. I don't need to know some function like here, like back here, like not that, but this. You might say, I don't care. I don't care what the precise answer is. I just need to know so that I can complete my calculations. I need to know what's going to happen when x equals 3 or whatever it is. And I don't really care about the actual closed form of the function. And so oops, I'm in low power mode now. Wow. Well, we better finish quick before the iPad goes dead. So here's the idea is you have a differential equation, and this is first order. It's got to be first order differential equation. So first order, and you have an initial condition. And what you're going to do is you're going to predict the future based on this initial condition. We've already done this. We've already done this with our slope fields. Do you remember we did this sort of thing? And in fact, on the last test, I had this slope field that you did, and you did a great job drawing various lines through the slope field. Like, well, some of you did a good job. Some of you didn't do as good of a job. But you know, you just want to kind of go with the flow. And here I didn't quite go with the flow, did I? This probably should be angled up a bit. But you just want to go with the flow. Well, Eulers' method, which is the numerical method that we're going to study now, is very similar to this. You have a slope field, and you're going to approximate your solution based on that slope field. So here's the idea, is you have a differential equation, and you have an initial condition. That differential equation will produce a slope field. I guess I've already got it zoomed in, or the book did. And so that slope field, if you zoom in on this one point, your initial condition, you have a slope. So you can be sure that whatever solution, which you've got the solution embedded in that slope field, that solution will point in the direction of the slope at that point. So the big idea behind Eulers' method is that if you don't happen to know what this solution looks like, you could, at the very least, you could say, okay, let's go in that direction a little bit. And how little is the bit? Well, maybe you'll just go a little step, like half of a unit, or 1/4 of a unit, or maybe 1/10 of a unit. Just go a little bit in this direction, and then let's start fresh and pretend that that's our initial condition. So let's actually draw something like this. Here we'll take a nice easy differential equation. dy over dx is equal to y plus x, just to make it easy. And let's suppose that our initial point, y of 0, is equal to 1. And then furthermore, we need to know how much of a step we're going to be doing. And so where is I just want to make sure I use the same letter. I don't see a letter here. I'm going to use delta x just so that we'll use this. Delta x is going to be 1/2. Okay, so This, by the way, is a linear differential equation. We can solve this. There's no reason why we can't solve this, but I just wanted to show you how this works conceptually. It's really not too difficult to implement. So we're going to start right here. And then this delta x says, oh, first of all, I need to know the slope. So at that point, this is 1 unit up, 0 units over. So here's y, here's x. And let's see, I'll mark off 1/2, 1. There we go. So maybe what we want to do is, perhaps for whatever reason, I need to know what the prediction of this function, where do I think the function will end up when x equals 2? I'm over here, and I want to know what's going to be happening over here. So what we'll do is we'll compute the slope. So let's find someone to compute the slope. You can compute the slope. So you're going to plug 0 in for x, 1 in for y. Just so you know, while I find my randomizer. A-solve, do you know what happens when you plug 0 in for x and 1 in for y right here? Yeah, very good. So dy over dx is 1 plus 0, which is just 1. So you have a slope of 1. So I'm just going to follow that line until I get to x equals 1/2. So I need to figure out what are the coordinates of this point. Obviously 1/2. But given that the slope here is 1, so that's the slope, can you tell me what that point is? Like, how high is that point? Does anyone know offhand? There's an easy way to do it, but you might be able to just do it by eyeballing it. Remember, it's a slope of 1. What's that? I heard a 1/2. So you go slope of 1, rise over run, go over 1/2. Yeah, 3 over 2, thank you. Sorry, I need to pick people at random, I guess. Okay, so now I need to come up with a new dy over dx. So my new dy over dx is going to be the new slope. So Claire, you get to do this slope. So go ahead and do it, and we'll get it in just a minute. Oh, you got it? Yeah, what is it? It is 2. Very good. So it's y is 3/2, x is 1/2, and you get 2. So you're using this formula here for the slope. And so it's a little bit steeper now. That really doesn't do it justice, does it? I don't think I will be able to do it justice. I'm going to have to start fresh. Give me a sec. So we'll just shrink things down. So here's the first slope of 1/2. There's our new point. And then we steep it, get a little steeper. And so the slope here is 2. So now my new point will be 1. And then what is the y value? So remember, slope is 2 now. So here's the new slope. So any guesses about where we are now? How high we are? 5/2. Very good, because if you go over 1/2, you're going to go up 1. And so you're adding 1 to the y value. So it's 5/2. This gives us a hint as to how we're going to do this. So now the next thing, we're going to do another slope, dy over dx. And so get the slope based on that point. So this one's going to be extra steep, but let's do one more. Max, you know what the slope is, don't you, if you plug 1 and 5/2 into this differential equation? Yeah, that's super steep, isn't it? So super steep. I'm going to, yeah, well, I don't even want to draw it. So I'm just going to conceptually think about it. So if we think about this, we're moving over another 1/2. So this is the next point. So let's take the old y value and add to this 1/2 of the slope. Isn't that what we've been doing all along? We started with 1, and we added 1/2 of this slope. This slope was 1. So 1 plus 1/2 times 1 was 1.5. And then we took 3/2 plus 1/2 times the new slope. The new slope was 2. So that became 5/2. Now we're going to do 5 halves plus 1/2 times 7 halves. And we'll do that until we get to wherever it is that we're going. So I guess I can finish calculating this. 7/4, 10/4, so 17/4. So that's the next point. It's up here somewhere, whatever. And then the last point is going to be way up here somewhere because the new slope is even steeper. I should have picked a different differential equation for this example. But that's the idea. We're going to do this over and over again until we get to where we want to go. Okay, so here is a picture of what we're doing and a picture which will explain the formula. So they use h instead of what I used was delta x, but it's the same idea. You've got your initial point here. You're going to go along the slope. You compute the slope, and you go over h and up however far you need to go. So, so this is x1 is the next point, and the next 2 is the point after that, and so on. So that's kind of a picture of what's going on. Now, we will have to worry at some point about the fact that we're not going to have the correct number, because and obviously the bigger you make h, the worse the error is going to be. So if you have a little small value for h, you'll be able to take little tiny steps and probably do a pretty good job. But in practice, you're not going to want to do that on a quiz or on a test or on a homework. So on homework, it's going to be big steps, bad error. So where's the actual Eulers method? Here it is right here. So here, that's delta x. So the new y value is the old y value plus the step size times the slope. This is the slope. So remember, we have this, this differential equation is dy over dx is equal to that function. All right, so let's see. I've got this that yeah, we might as well show you this. So just a couple of things. So there's this differential equation. Let's do the first step. Just a minute. I need to know. I can't see without doing this what the step size is. Ooh, wow. 0.1. Well, why not? Yeah, let's do 0.1 for the step size. So h, I'll use the way that the book does it, 0.1. And I just want one step, but I'll show you what it looks like with 5 steps and more. But I just want to, let's do one step for now. So do one step of this. So remember what, whoops. Remember what you're going to do is you're going to compute f of 2, 4. By the way, f is this thing right here. That's f. So that's going to be the slope. And then the new y is equal to the old y plus the step size times the slope. So there's what we're doing. So let's get the, first of all, plug 2 and 4 in. We'll get that first. I'll give you a minute. Shouldn't be too hard. You probably can do it in your head. Well, Rachel, you're the only Rachel here. What did you get when you plugged 2 and 4 into that function? Or you're plugging now? Yeah. All right. Yeah. Sorry, I'm rushing you. You can take your time. So let me know when you got it. I think you're off by just it's 0.4 times the x squared. Yeah, I think you left the decimal off. Yeah, 1.8. Very nice. So that's 1.8. So it's just 0.1 times 4, square root of 4, plus 0.4 times 2 squared. That's what she did. Very nice. And now what we need to do is we need to figure out the next point. So the next point will be what you get when you take the old y value, that's 4, whoops, 4, come on, plus the step size times the slope. So go ahead and do that if you have a calculator. If not, you'll just have to do it in your head. This will be y1. Haven, were you able to do that? What do you got? Did you say 4.18? Very nice. Okay, so the initial value is this. Then we get to 4.18. Let me show you a table of all of the values up to 2.5. And that's right here. So there's that 4.18. And if you were to do this again, you would get this, and then this, and this, and this. So this is the predicted value of the function when x equals 2.5. So that's what this is used for, is it's used to predict the value for a function without going through the trouble of actually solving the differential equation. Now you might say, well, that 0.1, if it was smaller, you'd be taking little baby steps and maybe you'd be closer to the truth, and indeed you are. And here's the closer to the truth. Notice that it's not terribly far away from this, but so this is, you're taking 10 little tiny baby steps instead of those 5 larger steps. And that's a little bit closer to the truth. Let me see, did I put the truth here? Oh, I don't have the truth. Well, we could get the truth at some point. Let me just see if I have any graphs, because the graphs are really interesting. Oh, I don't have graphs. I'll have to bring graphs next time, because when you graph these things, you can look at them in the book. You'll see that the like if you have smaller step size, the little baby steps, you stay much closer to the truth than if you have bigger steps. All right, so it'll take me a little bit to put the homework online. I don't think it's up yet. It might be there. I can't remember. But if it isn't, don't worry. I'm doing that after the day is done. So stick around if you want to chat. Otherwise, I hope you have a great